Imagine two immensely powerful supercomputers locked in this relentless, high-stakes game of cat and mouse.
Oh, yeah. The ultimate adversarial loop.
Right. So one of these machines is acting as this master art forger, trying to generate a completely synthetic reality from scratch. And the other machine is acting as the world's greatest detective, analyzing every single pixel to catch the forgery.
And they just iterate millions of times.
Millions of times, yeah. They're constantly trying to outsmart one another until eventually the detective can no longer tell the difference between the forgery and reality.
Which is wild because what you just described isn't science fiction at all. I mean, it is the fundamental architecture powering the current wave of generative artificial intelligence.
Welcome back to the deep dive. For you listening, our mission today is to completely demystify the architecture that makes that kind of digital cat and mouse game possible.
We are going to really get into it.
We are. We're exploring a really comprehensive foundational primer published by Icica, and they're a global community focused on digital trust and governance. The document is titled Artificial Intelligence, a primer on machine learning, deep learning, and neural networks.
And I have to say, it is a remarkable breakdown.
It really is.
Because it just refuses to let AI remain a black box. It strips away all the buzzwords, and it forces you to look at the actual underlying mechanics. Like, how does a machine actually group abstract concepts together?
Right. Or how does it adjust its internal logic when it makes a mistake?
Exactly. How does it process a massive grid of visual data or, remember the beginning of a paragraph by the time it finally reaches the end?
And we are going to unpack all of that today. We'll be moving step by step from the foundational math of just sorting raw data all the way up to the creation of these synthetic brains that can generate totally novel ideas.
And we're keeping it grounded.
Completely grounded. No intimidating jargon without an immediate, clear explanation of how it mechanically works.
Because to understand how a machine can generate a totally new reality, we really have to start with how a machine organizes the reality that already exists.
Yeah, that makes sense.
Before any kind of active learning can happen, there just has to be a structure.
Which means we need to talk about some data science fundamentals. Specifically, there's a concept the text refers to as agglomerative hierarchical clustering.
It's quite a mouthful.
It is, yeah.
Yeah.
Now, I know you listening are probably familiar with standard sorting algorithms, but this bottom-up approach is mechanically very distinct.
Very distinct, yeah. In standard top-down clustering, you might start with a massive data set and just tell the algorithm, hey, slice this into 5 groups.
Right.
But agglomerative clustering goes in the exact opposite direction. You start with your massive data set, let's say 1 million individual data points.
Okay, 1 million points.
The algorithm begins by treating every single data point as an isolated, totally independent cluster. So 1 million points equals 1 million clusters.
Okay, let's unpack this. It's basically like 1 million people standing in a giant open field, and everyone is just an island. Nobody is grouped together yet.
Exactly. That's your baseline.
Yeah.
And from there, the algorithm begins its iterations. It scans the entire field to find the 2 data points that are the most similar.
Just 2.
Just 2. It merges those 2 together into a single cluster. So now you have 999,999 clusters.
Wow, okay.
Then it repeats the process. It finds the next closest pair, merges them, and it just does this iteratively until all 1 million points have been swallowed up into one massive unified cluster.
Okay, wait. I have to stop you there because similar is a very human concept.
It is.
Like if I look at a crowd in a field, I can group people by who is wearing red shirts or, who is standing near the stage. A machine doesn't have that kind of intuition. So how is it mathematically defining similar?
That is the big question.
Yeah.
It calculates similarity using very rigid distance measurements. And the primer specifically highlights Euclidean distance for this.
Euclidean distance?
Yeah. If you plot 2 points on a graph, the Euclidean distance is just the straight line measurement between them. The shorter that line is, the more similar the points are.
I mean, I follow that if we are plotting actual physical coordinates on an X and Y axis, but what if we are clustering something entirely abstract?
Like what?
Like financial records or user behavior on a website. There is no physical map to draw a straight line across for that.
Ah, well, that is where the math scales up into multi-dimensional space. You aren't limited to just a flat 2D map.
Right.
So if you were analyzing user behavior, The amount of time spent on a page, well, that could be the x-axis. The number of clicks could be the y-axis. The geographic location could be the z-axis.
Oh, I see.
You can literally map 50 different behavioral variables into a 50-dimensional space. And the algorithm still just calculates the straight line Euclidean distance between data points in that abstract space to figure out which two user profiles are mathematically closest to each other.
That is wild. And it does this exhaustive calculation for every single unmerged cluster over and over again until everything is one giant group.
Yep.
That sounds incredibly computationally heavy, but also honestly a bit useless at the very end.
How so?
Well, if the final result is just one giant cluster that contains all the data, what have we actually achieved?
Ah, right. But the value isn't in the final unified cluster at all. The value is actually in the history of how the clusters merged along the way. Data scientists visualize this whole history using something called a dendrogram.
A dendrogram, the upside-down tree diagram, right?
Exactly. Think of it like a family tree. At the very bottom, you have the individual leaves. Those are your starting data points. And as 2 points merge, lines draw up from them and connect, forming a little branch.
Okay, I picture that.
But the critical piece of information on the dendrogram is the vertical height where that connection actually happens, because the vertical axis measures the Euclidean distance.
So if 2 points merge really low down on the y-axis, that visually represents that they were incredibly close in that multidimensional space.
Yes, precisely. And on the flip side, if you have 2 large branches that don't finally merge until the very top of the dendrogram, well, it tells you that those 2 broad groups of data are fundamentally very different from each other.
That makes a lot of sense.
And the beauty of the dendrogram is that a data scientist can just look at this visual history and draw a horizontal line across the tree at any height they want. Wherever that line intersects the vertical branches, that dictates the final number of clusters you end up using for your analysis.
Okay, that definitely clarifies the structure. So agglomerative clustering and dendrograms are brilliant for finding the natural fault lines in raw information. But fundamentally, I mean, this is just passive grouping.
It is.
The algorithm isn't changing its worldview. It's just blindly executing a distance formula until the room is sorted. If we want an AI that actively learns, we need a different architecture entirely.
This raises an important question, right?
Yeah.
Because to get there, we really need to abandon rigid mathematical rules and look to biological inspiration. We have to design systems that actually mimic the human brain's iterative learning process.
Because humans don't learn by calculating the Euclidean distance of everything in the room all at once. We learn through trial, error, and adjustment. The text notes that human knowledge builds over time. You know, we try something, we fail, we slightly adjust our approach, and we try again.
And that iterative process, that is the entire foundation of neural networks, or NS Chapter 4 dives right into this. To build a synthetic brain, the primer introduces the foundational building block of the whole thing, the perceptron.
Basically, the digital equivalent of a neuron.
Exactly. So a biological neuron takes in electrical signals from its neighbors, and if the combined signals cross a certain threshold, the neuron fires an action potential down its axon to the next set of neurons.
Right.
The perceptron replicates this mathematically. It takes in multiple numerical inputs. But crucially, it assigns a specific weight to each input.
Meaning, it decides which inputs are more important than others before it even makes a decision.
Yes. It multiplies each input by its designated weight, it sums them all together, and then it passes that final sum through what's called an activation function.
Okay.
And that function decides what signal, if any, it should output to the next layer.
But a single perceptron is essentially just making a binary choice, right? To achieve deep, nuanced learning, the source outlines the architecture of the multi-layer perceptron, or the MLP.
Right, the MLP is really the workhorse of deep learning. The structure is broken down into 3 distinct areas. First, you have an input layer, which receives the raw data.
Yeah.
Then you have an output layer, which provides the network's final prediction. And sandwiched right between them, you have the hidden layers.
And we are talking about a fully connected network here, right?
Yes.
Meaning, if I have 100 perceptrons in hidden layer A and 100 perceptrons in hidden layer B, every single node in layer A is wired to every single node in layer B.
Exactly. And that dense web of connections is really where the complexity lives. There are 2 primary processes of operation within this web. The first is feed-forward propagation.
Feed forward.
Yeah. This is basically the network taking a guess. Information flows strictly in one direction, from left to right. The data enters the input layer, it gets multiplied by the weights, passes through all those hidden layers, and finally produces a result at the output layer.
But the very first time it does this, its guess is going to be completely random, isn't it? Because the network hasn't learned anything yet.
Totally random. The initial weights assigned to all those connections are usually just randomized numbers. So yes, the first feed-forward pass is essentially an educated guess that is almost certainly wrong.
Which brings us to the actual mechanism of learning. How does a blind guess transform into intelligence? Because the text points to the second operational phase for this, which is backpropagation.
Backpropagation is the network realizing it made a mistake and actively rewiring itself to do better next time.
Yeah.
Once the output is generated, the network compares its guess to the actual correct answer.
Okay.
The difference between the two is calculated as the loss, or the error.
So what does this all mean? Let me try to ground this with a concrete analogy because the mechanics here are just so crucial. Imagine you are trying to hit a golf ball, but you are completely blindfolded.
Okay, how are these?
Your stance, your grip, the swing path of your club, those are your inputs and your weights. You take a swing, that is your feed-forward propagation. But because your setup was totally random, you miss the ball entirely.
We've generated a massive error.
Right. Now, someone takes your blindfold off for a second and says, hey, you missed the ball by 3 feet to the left.
So that is the loss function.
Exactly. You now know the exact mathematical distance of your failure. To fix it, you don't just blindly swing again, you use backpropagation. You start from the point of failure, the club missing the ball, and you work backward through your body mechanics.
You are adjusting the weights of your stance and your grip.
Yes. You adjust your grip by just a few millimeters. You shift your weight slightly to the right foot. You change the angle of your shoulders. You iterate.
Right.
You take another swing. Feed forward. You miss by 2 feet. Lost function. You work backward. Adjust the grip slightly more. Backpropagation. You swing. You miss by 1 inch. You adjust. You swing. And eventually you make perfect contact.
That is a perfect way to visualize it. And that iterative process of adjusting the weights to minimize the error is driven by a mathematical engine called the gradient descent algorithm.
Gradient descent. That's such an intimidating term. But mechanically, what is it actually doing inside the network?
Think of the network's total error as a rugged, hilly landscape. The goal of the neural network is to reach the lowest possible point in the deepest valley, because that represents zero error.
Okay, so a valley of zero error.
The gradient is simply the slope of the hill at the network's current position. Gradient descent measures how steep the error is and dictates the direction and the size of the step the weights need to take to move downhill toward that valley.
And it just continually calculates that slope and updates the weights after every single feed-forward pass.
Exactly.
But wait, if we are just multiplying inputs by weights and adding them up layer after layer, isn't that essentially just a massive chain of linear equations?
That is a highly critical observation, because if a network only uses linear math, 100 hidden layers are mathematically no more powerful than a single layer.
Wow.
Yeah, you can't learn the complex, curved, organic patterns of reality with straight lines. To break that linearity, the architecture relies on activation functions.
Okay, so these act as the nonlinear filters at the end of each perceptron.
They do. They transform the linear sum before passing it to the next layer. And the primer highlights a very specific activation function used at the very end of the process in the output layer. It's called the softmax function.
Softmax is fascinating to me because it solves a huge translation problem. Like, the raw math coming out of the final hidden layer might be completely arbitrary. Node A outputs a 14. Node B outputs a -2. Node C outputs 105.
Right, which means nothing.
Exactly. That doesn't tell a human anything useful at all.
So softmax takes those arbitrary, wildly varying numbers and squashes them into a normalized probability distribution that always adds up to exactly 1.0, or 100%.
Oh, that's brilliant.
So instead of receiving a 105, the output layer tells you, I am 85% confident this image is an apple, 10% confident it's an orange, and 5% confident it's a pear.
And that transition to discussing images is perfectly timed, because this is where the basic MLP architecture hits a massive roadblock.
It really does.
We've established how an MLP learns to adjust its weights, but feed-forward MLPs require a one-dimensional list of inputs. If I feed a high-definition photograph into an MLP, say, an image that is 3,000 by 4,000 pixels, well, that's 12 million pixels.
Right.
If each pixel is connected to thousands of nodes in a fully connected hidden layer, the number of mathematical connections spirals into the billions instantly.
Instantly. The computational load would just freeze the system. A fully connected MLP simply cannot process complex, high-resolution spatial data like that. And this bottleneck led to one of the most transformative breakthroughs in deep learning, which is detailed in Chapter 5.
Convolutional neural networks, or CNNs.
CNNs. They are the architecture of synthetic sight. They are literally how autonomous vehicles see the road and how medical AI scans X-rays. And they solve that pixel problem by fundamentally changing how the network looks at the data.
How so?
Well, a CNN does not look at every single pixel simultaneously. It looks at the image the way a human might scan a very large painting by focusing on small, localized patches.
Okay.
The architecture is split into two distinct operational phases. You have the hidden layers, which handle feature extraction, and then the classification phase.
Let's really dig into the hidden layers first, because this is where the magic of feature extraction happens. The core loop here is convolution, followed by a ReLU activation function, followed by pooling.
Yes. So the convolution operation relies on a filter. It's a small matrix of weights, typically just a 3x3 square. This filter slides or convolves across the entire image.
So it's moving across the picture.
Right. It stops at every single 3x3 patch of pixels to perform a mathematical operation.
And the source text actually gives us a fantastic granular breakdown of this exact math using a specific filter called the Sobel-Jix filter.
Yes.
Which is designed to detect vertical edges. Let's really walk through this because understanding this math is the absolute key to understanding how an AI sees.
What's fascinating here is that it's all just basic arithmetic. Imagine we've paused the filter over a 3x3 patch of pixels on an image of an apple. A computer views those pixels simply as numbers representing color intensity.
Great, from dark to light.
Exactly. So in our patch, let's say the top row of pixels has values of 8, 5, and 10. The middle row is 20, 16, and 20. And the bottom row is 20, 14, and 10.
Okay, so we take our 3x3 Sobel-Jix filter and we lay it directly over that patch of pixels. The weights of the Sobel filter are fixed, right?
Yes, they are fixed.
So the left column is entirely negative. It's -1, -2, -1. The middle column is entirely zeros, 0, 0, 0. And the right column is positive, 1, 2, 1.
Now, to process the patch, we simply multiply the overlapping numbers and add all 9 of the results together.
Let's do it.
Starting at the top left, the filter is -1 multiplied by the pixel value 8 is -8.
Top middle, the filter 0 multiplied by the pixel 5 is just 0.
Top right, filter 1 times pixel 10 is 10.
Moving to the middle row, middle left, filter -2 times pixel 20 is -40.
Middle center, filter 0 times pixel 16 is 0.
Middle right, filter 2 times pixel 20 is 40.
Bottom row now, bottom left. Filter -1 times pixel 20 is -20.
Bottom center, filter 0 times pixel 14 is 0.
And finally, bottom right, filter 1 times pixel 10 is 10.
Okay, so now we add that all up. We have -8 plus 0 plus 10 plus -40 plus 0 plus 40 plus -20 plus 0 plus 10. The total sum of all that is -8.
Right. We have taken an entire 3x3 patch of the image and mathematically compressed it into a single new value, -8.
And that single number becomes a pixel in a brand new filtered version of the image called a feature map.
Exactly.
We really need to linger on the mechanics of why that sum is -8 because it is the aha moment of computer vision. Look at the weights of that Sobel filter we just used. The middle column was entirely zeros.
It was.
That means the math completely ignored the center pixels of the image patch. The left column multiplied the pixels by negative numbers, and the right column multiplied the pixels by positive numbers. The filter is literally just calculating the difference in pixel intensity between the left side of the patch and the right side of the patch.
Exactly. If the left side is dark and the right side is bright, you get a large number, either positive or negative. That mathematical difference tells the network that there is a sudden change in contrast. And a sudden change in contrast is the physical definition of an edge.
Wow, and what if the filter slides over a patch of the image that is just a solid block of color, like the smooth, uniform red skin right in the middle of the apple?
Well, if the pixels on the left are identical to the pixels on the right, the negative multipliers on the left will perfectly cancel out the positive multipliers on the right. The final sum will be 0. The network knows there is no edge there. It's just empty space.
It's honestly astonishing that the simple grid math is what creates sight. But the network doesn't use pre-programmed filters like the Sobel for everything, does it?
No. Through backpropagation, the CNN actually learns what numbers to put in these 3x3 grids. In the early layers, it learns weights that detect simple lines and edges. But in deeper layers, it combines those edge filters to detect curves, textures, and eventually complex shapes like the stem of an apple or the wheel of a car.
Amazing. So after the convolution step, the output is passed through the ReLU activation function, which simply converts any negative values to 0 introducing that necessary nonlinearity we talked about.
Right.
And then it hits the pooling layer.
Yes, pooling is a downsampling technique. The primer mentions max pooling specifically. This takes a small area, say a 2x2 grid of the new feature map, looks at the 4 numbers, keeps the highest one, and just throws the other 3 away.
But I have to push back on the logic there.
Okay.
We are trying to analyze an image in really high detail. If max pooling throws away 75% of the data in that 2x2 grid, aren't we destroying the exact structural details the network needs to identify the object?
It definitely seems counterintuitive. But throwing away that data is actually what makes the network robust.
How so?
We want the network to achieve what's called spatial invariance. If you train a network to recognize an apple, and the apple in the training photo is perfectly centered, you don't want the network to only recognize apples that are perfectly centered.
Right. If it's in the corner of the photo, it's still an apple.
Exactly. Max pooling abstracts the data. It tells the network, hey, an important feature, like a curved edge, was found somewhere in this general 2x2 area. It forces the network to focus on the existence of the features, rather than memorizing their exact coordinate locations.
Oh, that's clever. It prevents the network from over-obsessing over irrelevant pixel placement.
Exactly.
So the image goes through convolution, ReLU, pooling, then another layer of convolution, ReLU, pooling. The spatial dimensions of the image get smaller and smaller, but the depth of the complex features extracted gets richer and richer.
Until finally, the hidden layers have completed their feature extraction. The network knows the image contains, say, red curves, brown cylinders, and specific light gradients. And now we move to the classification phase.
Right, because we have all these high-level features, but they are still structured in a multi-dimensional grid. To make a final decision, the text states we have to flatten the data.
Yes, and flattening is exactly what it sounds like. We take those grids of extracted features and literally unroll them into one single, incredibly long, one-dimensional column of numbers.
Because we have to feed this data back into a standard fully connected MLP, and MLPs can only accept a 1D input array.
Precisely. So we feed the flattened features into a fully connected layer. And this layer acts as the final logical synthesizer. It looks at all the extracted components and mathematically determines, given the presence of these specific curves and textures, the probability of this being an apple is extremely high.
And then the data hits the softmax function, and the network outputs its final confidence percentages.
Yep.
And all of that, the convolutions, the edge detection math, the max pooling, the flattening, the probability distribution, that happens in one single incredibly complex forward pass. It processes the visual input instantly.
It does. But that speed and that single-pass nature actually reveals a really profound limitation.
Because CNNs have no concept of time.
Exactly.
They process an image, spit out a classification, and completely wipe their memory. If you feed it a video frame by frame, it treats every single frame as an entirely disconnected universe.
Which is catastrophic if you are trying to analyze data where the order of the information is the most important part. Think about processing natural language. You cannot process a sentence in a single simultaneous flash because the grammatical meaning of the words at the end of the sentence depends entirely on the context established by the words at the beginning.
Right. We need an architecture with memory. We need a network that can understand sequence.
And that introduces recurrent neural networks, or RNNs. The primer details the architecture here, and the fundamental shift is the introduction of a loop within the hidden layers.
Let's break that down. In a feed-forward network, or a CNN, the architectural arrows only point forward. Input to hidden to output.
Right.
But in an RNN, the hidden layer has an arrow pointing back to itself. This loop allows the network to maintain an internal hidden state.
Yes, and to understand the hidden state, we have to look at how an RNN processes a sequence over time. The primer uses the sentence, "What color is your hair?"
Okay, so if a standard feed-forward network reads that, it processes what, and then forgets it. Processes color, forgets it.
But an RNN unrolls the sequence step by step. At time step 0, it receives the word what. It processes it, generates an output, and crucially, it updates its internal hidden state with a mathematical representation of the word what.
Then we move to time step 1. The next input is the word color, but the RNN does not process color in a vacuum. It takes the new input color and fuses it with the hidden state from the previous step.
Exactly. It is processing the word color through the lens of knowing it just read the word what.
It creates a new, updated hidden state that contains the combined context of what and color and passes that forward to the next step.
And by the time it reaches the final word, hair, The hidden state is this dense mathematical summary of the entire sequential context. It understands it is being asked a question about a physical attribute.
Here's where it gets really interesting, though. The theory is elegant, but the primer highlights a massive, fatal flaw in standard RNNs. It's called the vanishing gradient problem.
Oh yeah, this is a big one.
While the loop works for short sequences, if you ask an RNN to read a long paragraph, it essentially suffers from severe short-term memory loss. By the time it reaches the end, it has completely forgotten the beginning.
And I want to dig into why the gradient vanishes. Because it isn't a memory storage issue like a hard drive running out of space. It is a mechanical failure of backpropagation.
Let's break it down. We know backpropagation uses the chain rule to calculate the gradient, right? It multiplies the error backward through the layers to adjust the weights.
Yes. But in an RNN, you are backpropagating through time. You're moving backward through every single step of the sequence. If your sentence has 50 words, you are multiplying the gradient backward 50 times.
And the numbers we are multiplying are usually controlled by activation functions that output values between 0 and 1.
And therein lies the math problem. What happens when you repeatedly multiply fractions?
Oh, they get smaller.
Exactly. 0.5 times 0.5 is 0.25, times 0.5 is 0.125, then 0.0625. If you do that 50 times, the number becomes infinitesimally small. It literally vanishes.
The error signal just shrinks to essentially 0.
And once the gradient is 0, the network just stops adjusting its weights. It physically cannot learn the connections between early inputs and late outputs in a long sequence.
So to solve the vanishing gradient, computer scientists had to completely re-engineer the loop. We couldn't just have a simple, constantly overwritten hidden state. We needed a sophisticated memory management system.
We needed bouncers at the door.
Yes, we needed bouncers at the door of the memory state, controlling exactly what gets in and what gets kicked out.
That is the perfect conceptualization for long short-term memory networks, or LSTMs, and their cousins, gated recurrent units, or GRUs.
The architecture of an LSTM looks intimidatingly dense on paper, but the source text isolates the core innovation, the cell state.
Right. So in a basic RNN, the hidden state is subjected to heavy mathematical mangling at every single time step. It degrades. The LSTM introduces the cell state, which acts like a pristine high-speed conveyor belt running straight through the entire sequence.
Okay.
Information can travel down this cell state with minimal mathematical interference, completely bypassing the vanishing gradient problem.
But you can't just throw every single word of a paragraph onto the conveyor belt or it just becomes meaningless noise. You only want the critical context. This is where the LSTM deploys its gates to act as the bouncers.
The gates carefully regulate the flow of information onto and off of the cell state conveyor belt. They do this using specific mathematical operations, pointwise multiplication, pointwise addition, and two distinct activation functions, sigmoid and tan.
Let's unpack why it uses two different math functions, because the distinction is pretty vital.
The sigmoid function is the ultimate valve. It takes any input and squashes it into a number strictly between 0 and 1. If it outputs a 1, it means let 100% of this information through. If it outputs 0, it means completely block and erase this information.
And what about the tan function?
Well, tan takes inputs and squashes them between -1 and 1. It doesn't act as a valve, it acts as a normalizer. It ensures the mathematical values representing the actual data don't just explode into massive, unmanageable numbers as they move through the network.
The primer uses a really brilliant analogy here to make this concrete. Operating an LSTM is like reading a book. When you read a novel, you don't commit every single the and to long-term memory. You remember the protagonists, the location, the major plot twists.
Right. And as the plot changes, you actively discard outdated information to make room for new context. The LSTM replicates this cognitive process mechanically using 3 specific gates.
Let's walk through the gates exactly as the source described them, starting with the forget gate.
Okay, so the forget gate looks at the previous hidden state and the current new input word. Its sole job is to decide what information currently on the cell state conveyor belt is no longer relevant.
So, to apply the book analogy, imagine you are reading a chapter focused on a character named John. The cell state is carrying the context. John is the main character. But you turn the page, and the new input sentence reads, Sarah entered the room. She was the new protagonist.
Right.
The forget gate analyzes this new input and realizes the context about John is obsolete. It passes the John data through a sigmoid function, which outputs a 0, effectively multiplying the John memory by 0 and erasing it from the cell state entirely.
Perfect. And once the obsolete data is cleared, we move to the input gate. The network now needs to add the new context.
The Sarah context.
Exactly. The input gate uses the sigmoid function to decide which parts of the new input are actually important, and it uses the tend function to create a normalized candidate vector of that new data.
It's the bouncer saying, yes, the fact that Sarah is the protagonist is highly relevant. Let's encode that. And then it uses pointwise addition to push this new mathematical context right onto the cell state conveyor belt.
Finally, the network has to decide what to output to the next step in the sequence. And this is handled by the output gate. The cell state has been updated, John is forgotten, Sarah is remembered.
Right.
The output gate passes the cell state through a tend function to normalize it, and then multiplies it by a sigmoid filter based on the current input.
So it extracts only the most immediately relevant slice of context from the updated cell state and sends it forward as the new hidden state. It is just a masterpiece of dynamic memory management.
And the text notes that GRUs operate on this exact same gating principle, right?
Yes. GRUs, or gated recurrent units, are a slightly more streamlined architectural variant. Instead of separate forget and input gates, a GRU combines them into a single update gate. They achieve highly comparable results to LSTMs in really complex tasks like speech recognition and language translation, but they require a bit less computational power to train. Okay, let's take a breath and survey the landscape we've covered. We started with agglomerative clustering, teaching a machine to find distance-based boundaries in abstract space.
Yep.
We built MLPs using feed-forward guesses and backpropagation gradient descent to learn from failure. We constructed CNNs using convolutional filters and max pooling to give the machine spatial sight. And we unrolled LSTMs using sigmoid gates to give the machine a nuanced sequential memory.
We have meticulously assembled all the individual sensory and cognitive components required for a highly advanced analytical intelligence.
But analytical intelligence is ultimately reactive. It looks at a picture and says, apple. It reads a sequence and translates it to French. We now arrive at Chapter 6 of the AISACA primer. Generative AI.
This is the big shift.
What happens when we take all of these architectural breakthroughs and wire them together to make a machine create something entirely unprecedented?
We transition from analysis to synthesis. We enter the domain of generative adversarial networks, or GANs.
GNNs are where the architecture feels almost psychological. It isn't just one neural network trying to solve a puzzle. It is a dual network system. Two distinct neural networks forced into a literal mathematical competition.
It is a zero-sum game played by a generator and a discriminator.
This brings us right back to the scenario we opened the show with. The source text really leans into the classic analogy here. The generator is the forger and the discriminator is the judge. Let's define the parameters of this game.
Okay, so the generator's objective is to manufacture fake data, whether that is a synthetic image of a human face, a fake audio clip, or generated text. It starts with nothing but a matrix of random mathematical noise, which the primer labels Z.
Okay, noise Z.
The generator maps this noise and forces it through its layers, attempting to transform it into structured fake data, which we label X.
But in the beginning, the generator has absolutely no idea what a real human face looks like. It's just twisting random noise into chaotic pixels. How does it learn to forge reality?
It relies entirely on the feedback of its adversary, the discriminator. Now, the discriminator is typically a highly trained convolutional neural network, exactly like the ones we broke down in Section 3.
Oh, that connects perfectly.
The discriminator is fed a mixed batch of data. Half of it is authentic, real-world data. The other half is the fake data X produced by the generator.
The discriminator acts as the detective. It processes the images through its filters and outputs a binary classification for every single file, real or fake.
And the primer outlines the life cycle of this adversarial training process in 4 distinct chronological phases, A, B, C, and D.
Let's walk through them. In phase A, the system is naive. The generator takes random noise Z and produces an image that looks like, a static-filled television screen.
Right.
The discriminator, even with basic training, easily flags it as a blatant forgery.
But here is the critical mechanism of the JANA. When the discriminator catches the fake, it doesn't just reject it. It calculates the loss function and backpropagates that mathematical error directly into the generator.
It's literally the detective explicitly telling the forger exactly how they got caught. I knew it was fake because the pixel contrast around the eyes was entirely unnatural.
Which initiates phase B. The discriminator is improving because it is analyzing more data, but simultaneously, its feedback is becoming highly precise, which allows the generator to drastically adjust its weights and improve its forging technique.
They are locked in an arms race. In Phase C, the dynamic severely shifts. The generator has absorbed millions of microcorrections. It is no longer outputting static, it is generating complex shapes, skin textures, and lighting gradients. The generated data X is beginning to closely overlap with the mathematical distribution of the real data.
If we connect this to the bigger picture, the forger is starting to successfully fool the detective. The discriminator's CNN filters are struggling to find the mathematical anomalies that distinguish the fake from the real.
And then the system reaches Phase D.
Phase D is the state of equilibrium. It is the holy grail of GN architecture.
At equilibrium, the generator has perfectly mapped the real data distribution. It is producing synthetic images that are so structurally, texturally, and mathematically flawless that they are indistinguishable from reality. The discriminator, the internal mathematical judge designed specifically to catch fakes, is completely blind to the forgery.
Right, its accuracy drops to 50%. It is merely guessing coin flips at that point.
Wow.
At this stage, the GN is considered fully trained. The adversarial loop is complete. You can detach the discriminator, and you are left with a generator capable of summoning entirely new, photorealistic realities from random noise on command.
This brings us to a fascinating and frankly daunting endpoint, because we have spent this deep dive entirely focused on the internal math, the weights, the convolutions, the sigmoid gates. But the technology does not exist in a vacuum.
No, it doesn't.
To fully honor the scope of the AISCA primer, we need to put on our instructor hats for a few minutes and examine the real-world fallout of reaching this GN equilibrium, because the final chapter, Chapter 7, is dedicated entirely to this.
It is. The primer doesn't end with the mathematical triumphs of generative AI. It dedicates Chapter 7 entirely to the resulting risk and governance landscape. And as instructors looking at this, it is a landscape completely disrupted by the capabilities we've just outlined.
Let's step through the implications systematically, precisely as the source structures them, starting with the ethical landscape and societal risk. We just detailed how a GAN can generate indistinguishable synthetic reality. When that capability scales globally, the ethical foundation of shared truth begins to fracture.
The primer flags this societal risk prominently. If generative models can produce hyper-realistic video and audio of public figures saying things they never said, the societal trust in digital media erodes.
It's the deepfake problem.
Exactly. The mathematical equilibrium we just celebrated becomes a vector for mass disinformation.
Which leads directly into the data security and privacy risk. These MLPs and GANs don't just learn from thin air. They require oceans of training data to establish their baseline of reality.
And that training data often includes sensitive, personally identifiable information, proprietary corporate data, or copyrighted material. The models absorb this information directly into their weights.
This is where the primer highlights the danger of IP leakage. If an employee feeds a proprietary software codebase or a confidential financial report into a generative AI to ask for a summary, that data doesn't just disappear.
Right. It can become embedded in the model's training parameters, potentially leaking out to other users in future outputs.
Which is why the governance frameworks stress the acute danger of weak internal permission structures. If an organization deploys an internal AI tool without rigorous, siloed access controls, a generative model could easily ingest and expose highly classified HR data to an entry-level employee simply because the AI had overly broad file permissions.
And as instructors teaching this material, we have to point out that the risks aren't just accidental leakage, they're actively malicious. The primer explicitly outlines the cybersecurity impact of AI, specifically citing the rise of AI in cybercrime.
We talked about how an MLP uses backpropagation to iterate and perfect a task. Hackers are now using those same iterative architectures to write polymorphic malware that constantly changes its code to evade detection.
Yes. The text mentions tools like PentestGPT. While designed for cybersecurity professionals to automate penetration testing and find network vulnerabilities, the exact same generative capabilities are leveraged by threat actors to automate devastatingly complex cyber attacks at a scale human hackers could never achieve manually.
It's literally the adversarial loop of the GAN leading into the real world. The cybercriminals build better generative attacks, and the security professionals must build better discriminative AI to catch them. Phase A, Phase B, Phase C.
Which necessitates the final topic of Chapter 7, the urgent demand for responsible AI frameworks. Organizations can no longer view AI merely as an IT tool. It must be governed with strict ethical oversight, continuous auditing of the training data for bias, and robust safeguards against both accidental leakage and adversarial exploitation.
Because the math will not govern itself. And that is the final provocative thought I want to leave you, our listener, with.
Yeah.
Think back to the climax of the Jan architecture, phase D equilibrium. We have successfully engineered a synthetic brain where the internal, highly sophisticated algorithmic detective is forced to admit defeat. The machine itself can no longer tell the difference between reality and a generative hallucination.
It's a sobering thought.
So as these models are deployed into our world, generating the news articles we read, the audio clips we hear, the code running our banks, if the machine's own dedicated neural network cannot spot the forgery, how are we, the human discriminators, supposed to tell the difference?
That is the big question.
Does our ability to manage the societal risk and the cybercrime implications outlined by AIAuditor rely entirely on our human capacity to somehow outsmart the ultimate algorithmic forger?
It is the defining governance challenge of this technological era. We have built the synthetic mind, now we must figure out how to live alongside it.
We absolutely must. Thank you for joining us on this deep dive. Keep exploring the mechanics behind the magic, keep questioning the digital world around you, and we will see you next time.